Okay, so now now we've actually written out the matrix equations for solving the field within one triangle. And so now we're going to talk about what happens if we have more than one triangle, because that's going to be more interesting. So we can now expand this out so we can have an unlimited number of triangles, but that would take a while to write up. So I'm just going to do it for 3 triangles and show you the process, so that because if you can write it out for 3, then you can write it out really for any number of triangles. So let's look at this a bit more. So expanding to 3 element problem. So if we have 3 elements, three triangles, 3 elements, we'll have 5 nodes, such as shown here. So they're sharing one line each. And so we have element 1, element 2, and element 3. So now we can, so these points are nodes. The points of the triangle are called nodes, and each of the triangles is called an element. So then we can make a table, and you could make a matrix in Matlab, for example, with this information. So you'd have the element number, and then you'd have the nodes, and you need to keep track of the node numbers. So in this case, they're being defined as counterclockwise. So there'd be node I, J, and K, like what we talked about with the single node, but now we have 3. So element 1 has nodes 1, 2, and 3. So it's just 1, 2, 3. And then element 2 is 1, 3, 4. And element 3 is 1, 4, 5. So we have 3 elements, but and with those 3 elements there's just 5 nodes. So we need to keep track of which element has which nodes. Yeah.
Doesn't matter where you start.
No, but it's probably good to start in a corner of the problem.
But for each given node, just like for element 2, if you were to say it's 3, 4, 1 instead of 1, 3, 4.
And as long as you're consistent with the starting point. I mean, the example I'll show in class next time is broken up into grids. So you have to have a consistent numbering system. So how you decide on that is up to you. But you have to. The important thing is to keep track of the node. What nodes are related to which element. So if you start on the bottom corner, and you could go up, or you could go to the right. This is I'm going to in the example I'll show tomorrow on Thursday. it's a grid. So there's much more advanced meshing approaches, like JMAG uses a much more advanced system, but the important thing is just to keep track of where they are. And with this simple triangle type of arrangement, we're just going to do it in blocks. Okay, so so we have these elements, these nodes, and then there'd be some current that could be associated with each node. With each element. Some current density. So now each of these nodes would have a particular vector potential associated with them. So vector potential value at each node point. So A1, A2, A3, A4, and A5. So then let's look at element 1 in the context of having 5 elements. So in that case, because we have 5 magnetic vector potentials, the stiffness matrix needs to be 5 by 5 in size. So the stiffness matrix will now be, so for triangle 1, we're going to have 5 by 5. Because we have nodes 1, 2, and 3, we're going to have matrix values in the first 3 by 3 part of the 5 by 5 matrix. Okay, because we've got vector potentials related to vector potentials at 1, 2, and 3, but nothing at 4 and 5, right? It's for element 1, for triangle 1, or element 1. So we have S11, and then I'm going to put subscript 1 for the element 1. Maybe I'll write this element rather than triangle. So we have S11, S12, S13, and then 0, 0. So, and then this here is A1, A2, A3, A4, A5. And so then here we have S2, S211, S221, S231, 0, 0, S311, S321, S331, 0, 0, and then this is 0, 0, 0, 0, 0. So that's element 1. So we've basically we've written out what we just solved before, but we've now put element 1 in a 5 by 5. So now element 2. Element 2 has nodes at 1, 3, and 4. So for element 2, we're going to have values at nodes 1, 3, and 4. So then we're going to have S11, 2, then 0, and then S1, 3, 2, S1, 4, 2, and then 0, like that. oh, I need to put the, whoops, we forgot the right side here. So the right side, so the right side of this stiffness matrix is the source currents, right? So in the most general case, we'd have currents density of all three elements, in all three elements. So let's do that. So then for the first one, we're going to have, it's at element 1, we're going to have current densities 1, 2, and 3 associated with those three nodes. And so it's over, because there's three nodes, we divide by 3. So we have 1, 1, 1, 0, 0. And then that's J1 delta over 3. Like that. Okay. So now back to element 2. So this is, on this side, you're going to have A1, A2, A3, A4, A5, and so again, going back, element 2 has nodes 1, 3, and 4, so we've got 1, 3, and 4. So then the next row is all zeros, because it's A2, and then also A5 is going to be zeros, right? So we can fill that out as well. And then the next two have values, so we've got A312, 0, sorry, S312, and then S332, S342, 0, and then S412, 0, S432, S442, 0, like that. And that's equal to the current in element 2. So on here now we have 1, 0, 1, 1, 0. Like that. Okay? So that's element 2. So you can see this is really good for a computer, but not good for humans to write out. So now the third one is, I guess I'll put it up here. Third element, element 3. So we're going to have values at 1, 4, and 5. So the first one is S113, 0, 0, S143, S153, like that. And we have A1, A2, A3, A4, A5, like that. And so element 2 and element 3 are not associated with nodes 2 and 3 are not associated with element 3. So we have zeros in these next two rows. And then the fourth row has S413, 0, 0, S443, S453. And then last but not least, F513, 0, 0, F543, F553, like that. And so then this is equal to 1, 0, 0, 1, 1 for the current density. So that's it. So you could see how you could define the number of triangles you want to have in your problem. That would then decide on the size of your stiffness matrix. then you would populate the stiffness matrix with the stiffness terms that are defined from the coordinate information that we wrote out, and you just repeat it based on the locations where the nodes are not zero. So the important thing is then you have to keep track of the coordinate positions, because that would be some coordinate values. So there has to be, in addition to this, there needs to be some coordinate position information. Okay, so if we've got each of these, we can then combine it together into a complete solution. So it's quite a sparse solution matrix. There's going to be some of the parts are going to have quite a few zeros. So we're going to have out here S111 plus S112. So I'm adding the three matrices together. Maybe I should write that here. Adding up three matrix equations. So that's what we're doing. So I'm adding this one up. We've got S111, S112, and S113. And they all contribute because all three elements share node 1. So plus S113. And then the next one is S121. And then we have, and the third one has got two terms here. So we have S131 plus S132. No, sorry, I circled the wrong one. It's this one. Yeah, so S131 plus S132. And then the next one is S142 plus S143. And then lastly, S153. And that's all multiplied by A1, A2, A3, A4, A5. So I'll just go over this so you have a record. So we have S211, S311 plus S312, S412 plus S413, S513. And then the second column is S221, S321, and then 0, 0. Then the third column is S231, S331, S332, S432, and 0. So I highly recommend you check this. 0, S342, S442 plus S443, and then S543. That's S543, yep. And then last column is got two zeros here, and then S453 and S553. Phew. So that's the stiffness matrix, and now that's equal to the currents, and we add the currents up as well. I'm going to go across to the next side of the board. So this is equal to 1 over 3, and so in here this is J3 times the area, which is the current. So here I'm just going to write it in terms of current. So we'll have I1 plus I2 plus I3, and then the second row only has I1, and then we have I1 plus I2, I2 plus I3, and I3, like that. And there we go. So then, you get to this, and you can take a big breath of relief. And so then you can see that this has the form of a matrix. So thus we have S matrix times A matrix equals a T matrix. So we can, and again, this S matrix would typically have quite a lot of zeros in it for a big problem. And so then we can solve for the magnetic vector potential at each node point by taking the inverse of this. And then you'll get the answer. Any questions on that? So what's the units for the S matrix? Do you think? So this is units of current, and magnetic vector potential has units of Webers per meter, because remember, flux is equal to the magnetic vector potential around the length. So flux has units of Webers, and this is a length, so the vector potential has units of Webers per meter. So then we have, so if we look at this, we have that, so that we have stiffness. This is Webers per meter, and this is equal to current. So we have amps meters divided by Webers, but remember that inductance is equal to flux over the current, which has units of Webers per amp, which is also known as henries. So here we've got Webers per amp, which is henries. So we've got meters over henries. And so remember that reluctance is equal to n squared over the inductance. And so turns doesn't have units. Inductance has units of 1 over henries. So the stiffness matrix is a bit like the reluctance. It's got units of reluctance per unit meter. If that's kind of interesting. Okay, now there's one last bit though. We're missing something. So remember we've got two parts to solving any problem. We've got, remember we have something like this that we wanted to solve. So if we have a problem here, and we define that this in certain regions we have we have this governing equation, there's one last bit that we haven't sorted out here. What's that? Boundaries. Yeah, so we need to talk about the boundary conditions briefly. But that's actually, thankfully, that's really easy. That only takes a very short part. So boundary conditions. I'm just going to talk about Dirac boundary conditions, where you just set a value on the boundary. So if the value of the vector potential on some part is known, some part, let me write that, some boundary, on some boundary part, no, I'll just put boundary, on some boundary is known, we can add this into the matrix formulation. For example, say we know that A2 is equal to 5. So at node 2, the magnetic vector potential is equal to 5, which would be really huge actually. It's usually in Miller values. So if this was equal to 5, then what would we do? Then we don't need to solve for the field at that node, because we know it. We're told it. So then we can look at our matrix here, and we've got A2 here, right? So that's the magnetic vector potential. That has to be 5. So then we come across this term here is multiplying by the A2. So we can replace that by a 1. I can easily do that on the board. And I've conveniently erased the part that I need to change. And so on the right side, we had the currents, which I now have to rewrite. But the second term is associated with A2. So if we come across and go and multiply, we need A2 to equal 5. So what does this have to be here? 3 times 5, right?
So that's actually 1 divided by that?
Yeah, 1. Because if you go multiply that, you'll get A2, and that A2 has to equal 5. Is 1 over 3 divided by 3 gives 5. And then this is I1 plus I2 plus I3 and I3. Does that make sense? So that's the boundary condition done. So you can easily the boundary condition is relatively simple. You just have to know if you have a problem where the boundaries are known on the edges, then you need to keep track of the values, the node points on the edges, and then once you've formulated your problem, you can go back and put in the ones where the vector potential values should be set, and then on the right side you put the value in that you want. Okay. Any questions on that? So next time next lecture I'll go over an example on the board on the computer where we solve a simple problem using this approach in Matlab. So and for this last 15 minutes, I just wanted to go over practical aspects of numerical modeling and what are the possible causes for error. So, accuracy of numerical modeling. So there are three sources of error that are unavoidable. They're going to exist. You can't escape it. So one possible error is, and if I wasn't recording this, I would ask you, modeling errors. So, for example, whoops, I made an error in spelling error. That's pretty good. So for example, assumptions, there's always going to be some assumptions. So, you know, the 2D, one example is that we're neglecting the 3D. The other types of assumptions maybe are more nuanced. You could have a 3D model, but there still be some assumptions. For example, assumptions made at the problem formulation. There's just a big, large number. Some basic ones are nonlinear problem assumed to be linear. That's really that will make a big difference in your modeling. That's what homework 2 looks at. And then another one is say eddy currents are neglected. There's core loss. That's extremely difficult to be accurate with. So there's the model that you use to account for the core loss in a machine is going to have inaccuracies. And then laminations. The machine is even if you model in 3D, you're not likely to model all of the laminations individually. So there's going to be modeling error because you don't account for that. So there's going to be a stacking factor. So there's just a lot of there's always going to be some modeling errors. Then another unavoidable error is truncation. Truncation or discretization errors. So this is with regard to the finite element modeling. So the mesh size. If you increase the number of mesh elements, you should get more accuracy. And so then the question is, how small or how large a number of elements should you go with? How do you know when your answer is right? Because there'll always be some truncation error, but you can be relatively sure that your answer is right by doing a bit of checking, and this would be really good to plot in your. You'll get extra bonus points for doing this. I don't think this was written in the question. You could, so you know the mesh number. So maybe the value you're wanting is the magnetic flux density in the air gap of the device that we're that we're looking at. So we're interested in the value of the magnetic flux density here. So now we divide this whole problem into lots of elements. But the question again is how many elements? So you could try not too many, and then you could calculate what the flux density is in, say, the y direction, and you might get this value here. Then you increase the number of elements, and it changes. It goes up. And then you increase the number of elements again, and it changes, but not as much. And you increase the elements again, and you keep doing that. And then at some point, that if you increase the number of elements more, you're really not going to get any change. And so then you can be relatively sure that the answer is right. If you don't get much change in the results for two different numbers of elements, then you can be relatively sure that at least your meshing is not causing a problem with the model. So that's a good way to check it. But because you don't want to, if you run your simulation and you get one result and then you increase the mesh and you get quite a difference in the result, then that should be a red flag that you need to try increasing the number of elements. So that's truncation error. So there's mesh size, but the other thing is that we talked about now. There's another more nuanced part to it. So mesh size is not the full story, because remember when we did the modeling, how did we model the triangle? We used a trial function, right? So we had our triangle, and we had the trial function here. So what if that's not accurate? If the trial function is not going to be perfect. So that's also going to lead to truncation error. But that can be significant. I mean, there used to be a lot more discussion of different trial functions, but now with the brute force method of having really powerful computers, you can just keep making the mesh smaller and smaller. And so even if the trial function is not the best type of trial function, is if you keep making the elements small enough, it's likely to give a good result. So now with the computers really quite powerful, you can this is not such an issue. But with 3D, the 3D trial functions could still have some role to play, particularly in that case. So the basis function, which is made up. The basis function is the weighting function is made up of the basis functions. So the basis function approximation. We're not, in this example here, we're ignoring squared terms, right? There's no squared terms in this. Okay, so that's unavoidable. There's going to be error in that. And then the third unavoidable error is round-off error. So round-off error. So this is not such an issue now with computers. So it's unavoidable computer round-off error. So this is very small now. So very small with today's computers. But it can have an impact if you, well, it would mainly have an impact if your code wasn't written properly. So there's this is a nice sort of, I'm going to draw a nice sort of picture to finish on. It's not to scale, but we could have here, again, the mesh size. And now this is opposite to how I drew it in the previous figure. So this is error here. Okay, so if we make the mesh size smaller, that means more elements. So bigger elements means less mesh, less numbers of elements. So making the mesh size, so this would be lots of elements. And here's few elements. So if we make the mesh size really small, the error is going to come down due to the discretization error, the truncation error. It's going to, the error is going to come down. That's what I discussed. But at some point, you're going to have so many, the mesh is so big that you'll get some round-off error. And this is not to scale. Let me do that in blue. So this black one here is the discretization error, and then this would be round-off error. But this is, again, so there'd be some minimum error point. But this is not to scale. So now the computer's having, being able to have much higher precision, the round-off error is reduced down. But it's a nice picture showing the trade-offs. Okay? All right, not to scale. Not to scale. Okay, I'll stop there. So, okay, so this is the project one, and it involves solving a two-dimensional problem in Matlab, and it should get you really thinking about the finite element and how it works. enjoyed doing this project when I was a student, so now I thought I'd let you guys try it. And so what it involves is you have basically two regions. You have region 1, which is this U shape here, that has a magnetic material which is set to 1000, the relative permeability. And then this air region in the middle and the top has a relative permeability of 1. And now the boundary conditions are where the interesting part happens. So on the left boundary along this side, you set everything to 0. So all the nodes on that side would be set to 0. And then on the right boundary on this side, you set the boundary to a value of 1 times 10 to the minus 3. And so that's the vector potential. That's the magnetic vector potential. And so then if you do that, if you have a difference in the magnetic vector potential from one side to the other, that creates a flux. And so you don't have to define the boundaries on the top and the bottom. If you don't define them, then it will be considered the natural boundary condition, and you'll see that the field will flow from the top down to the bottom. And the reason that it will do that is because, remember, I said that A dl is equal to the flux, the magnetic vector potential around a loop, right? We talked about this. So, because you can integrate remember, if you integrate the magnetic flux density over an area, that will equal the flux. And so you can replace the B with del cross A, and then using Stokes' theorem, it results in having a line integral. Now, in the 2D case, remember that if we have a 2D case where this is the flux is going through this rectangle, but in this case, if it's 2D, we don't have any depth into the page. So then we only have a magnetic vector potential on one side, which is in this case 0, and the other side, which is 1 times 10 to the minus 3. And so if we set the sides, we set this one side to be 0 and one side to be 1 times 10 to the minus 3, what that then tells the program is that a flux has to flow all the way through, all the way down the problem region with the same amount of field. And now what happens though is that because there's iron in these two, a magnetic material in region 1, the magnetic field will become distorted. It won't want to go from the top down through the air region. It will want to distort and go through the sides, because that has a lower relative permeability. And so your plot should show that. And you can, so now what I would suggest you do is you actually can, I would suggest you split up the problem. This is my suggestion. You have to solve the whole thing, but you can split it up by essentially the meshing can be split up into 5 regions. So you have the top region A, and then you have region B, C, D, and E. Now, if you look at the dimensions given, it's not to scale what's drawn. This here is only 1 millimeter, because it's supposed to be a. You can think of this as being the air gap of a machine, and this being the tooth, and this being the slot. And so you'd have a small air gap. Now you need to have quite a few elements in that air gap to model it correctly. So I would recommend you write it so that you can choose the number of elements. So you'd break this down into elements like that. Now it would make a lot of sense to make the element points, the nodes, coincide with these boundaries too. So you can make your triangles like this, for example. So you'd have triangles across here, but you could define how many you would want across the x-axis and how many along the y-axis, and then you can break them down in the sections. And so you could test it by having only a small number of triangles and then increasing them. And so you need to calculate what the energy is in the air gap. So I'll remember that B squared over mu naught gives the energy density. So you can use this relationship to calculate the energy. As you increase the number of elements, then your value for your energy should not keep going up. So it should, it should become some constant value as you increase the number of total elements in the code.